Hi class, let's prepare for exam 2. So starting off, we should definitely know the definition of a metric. So remember that a metric is a real valued function we label it D from the Cartesian product to R here, such that D satisfies the following properties. So the first is that D of AB is non-negative and D of AB is 0 if and only if A equals B. So what this tells us is that if the points are equal, their distance is 0, and if they're not equal, then there's some distance between the points. Here. The real value function is symmetric, so D of AB equals D of BA, and it satisfies our triangle inequality. Okay, let's look at an example here. So let D be a metric from a set X, on a set X, sorry, and let it be defined by the following. D of AB is 0 if A equals B, and 1 if A does not equal B. Now, this is what we call the discrete metric, but let's argue that it satisfies our properties. So clearly, so let's check. Clearly, it's non-negative for all points in X. Furthermore, by definition, D of AB equals 0 if and only if A equals B, right? This is how we defined our metric here. Okay, so it's easy to check. Let's put it here. Clearly, D of AB equals D of BA. So you can give a quick little argument on this for all A, B, and X. So let's finally check the triangle inequality. So finally, let A, B, and C be elements of X, and we need to verify the triangle inequality. So we're going to do this by cases. So case 1, assume A, B, and C are all unique, so they're not, none of them is equal to each other here, then by definition, d of AB equals 1, d of BC equals 1, and d of AC equals 1. Hence, d of AC, which equals 1, is less than or equal to 2, which is 1 plus 1, which is d of AB plus d of BC. Here, so we've shown that this statement is less than or equal to this statement here. Okay, case 2. Here. So case 1, so how I'm arguing this, case 1, none of them are equal. Case 2, one pair will be equal, and then I'll have case 3 where all of them are equal. So case 2 is a without loss of generality. Assume that A equals B. Right? Because these are just placeholders. A equals B, or A equals C, or B equals C. They're all very, very similar arguments. So let's just say without loss of generality, assume that one of the pairs is equal here. Okay, then d of AB, which equals d, which equals 0, d of AC equals 1, and d of BC equals 1. Here. Hence, d of AC, which equals 1, is less than or equal to 1, which is 0 plus 1, which is d of AB plus d of BC. So once again, we've argued that this statement is less than or equal to this statement. And in case 3, assume they're all equal, A equals B equals C, then d of AB equals 0, d of AC equals 0, and d of BC equals 0. Hence, d of AC, which equals 0, is less than or equal to 0, which is 0 plus 0, which is d of AB plus d of BC. So again, I've argued that this statement is less than or equal to this statement here. Okay, another thing we want to recall here, and we should know, is that the collection of all open balls of radius r here is, sorry, this is not, I didn't finish my sentence, is a basis for any given metric space. Here, right? These are the open balls remember that B of Rx is the set of all y such that y is in X and D of xy is less than R. Here. Right, so we can think of that, we have an X, we have a radius R, and so I'm in this open ball if my distance is less than that R. Okay, so that's a very useful fact as well here. We should also remember what it means to be Hausdorff here. Okay, so a space is a Hausdorff space if for all A, B, and X with A not equal to B, then there exists open sets U and V in X with A and U, B and V, and they're disjoint. So U intersect B is empty. Here. And let's look at an example. Any metric space, we'll call it XD, is a Hausdorff space. Okay, so let's argue this. So what we need to do is we need to pick our generic, right? This is my quantifier for all, so pick my generic. So let A, B be elements of the set that are distinct, so A not equal to B. Then, from our discussion of a metric, right, this is a metric, there's a distance between them. Right, so the distance between A and B is positive because they're not equal. It's only 0 when they're equal. What we can do is we can set a radius to be this distance over 2. Then clearly, A is in the open ball centered at A of radius R, and B is in the open ball centered at B of radius R. And these are clearly open sets because they're part of the basis, right? Basis elements are open sets. So what we need to do, we want to argue that they are disjoint. Here, right? So we need to satisfy, we found open sets in the metric space such that the 2 points are in the respective sets. And now we need to argue that they're disjoint. So for contradiction, assume they're not disjoint, right? So then we can find an element in the intersection, right? If this is not empty, then there's an element that exists in there. So hence, d of xa is less than r, and d of xb is less than r. Because x is in here, so the distance between a and the element is less than r. But x is also in here, so the distance between b and the element is less than r. But notice, by the triangle inequality here, that the distance between a and b is less than or equal to the distance between a and x plus the distance between x and b. But this is less than r plus r, which is 2r. But what was r? R, by definition, was dAb over 2. So this is 2 times dAb over 2, which is the distance of AB. And this is clearly a contradiction because we have that the distance between A and B is strictly less than the distance between A and B, which can't happen here. So a contradiction. So metric spaces are Hausdorff spaces. Here. Oops, this blue is not erasing very well today, so I will not use my blue and try another color. Okay, let's look at another example. And this is number 5 in section 6.1, found on page 136, and it states the following: the metric D is continuous. Right? Remember, D was a real valued function, right? This metric is a real valued function, and this problem here is saying that the function is continuous here. Okay, so going back, how do we show continuity? Remember that we need to take an open set here and look at its inverse image and argue that it's open here. But remember, a lot of times it suffices just to focus on the basis elements. What are our basis elements of R with the standard topology, Euclidean topology? Right? Remember, they're open intervals. So it suffices to show that D inverse of AB is open in the Cartesian product x cross x here, right? This is, remember, a basis element. Because any open set is the union of those, and we can pull out unions with inverse images, so we can just focus on the basic set here. Okay, so how are we going to argue that that's open? Well, remember, X is a metric space, right? We have this D, right? D is a metric, so X is a metric space. So X cross X is a metric space here. Right, because what they're going to do is they're going to take products of open balls here to be my basis. So what I need to argue is that this set is open by fitting an open ball inside of it. So I'm going to pick a generic point. So let xy be an element of the inverse image. Then this tells me that the distance of xy is r, where r is in this interval. Here. Notice that this is telling me if I'm in the inverse image, then when I push it forward, my distance has to be in here, right? That's what this is saying. So I'm labeling my distance as r, and my r has to be in this open interval AB. Here. Now, since AB is open in R, we may find epsilon greater than 0 such that R is an element of R minus 2 epsilon, R plus 2 epsilon, which sits fully inside of this set. Right? Remember, this is an open set, so my basis elements are open intervals, so I can find an open interval containing this point fully contained in this open set. And you'll see why I use this in a second here. Right? So this looks a bit strange, but you'll see traditionally you do the scratch work first and then put it together in your proof. So you'll see where that comes from and why I chose that in a second. Okay, so now xy is clearly an element of this open set in x cross x. Right, because x is part of this open ball, right? It's the center, and y is part of this open ball. It's the center. Both have this radius of this epsilon that we found, so that this thing fits inside of this thing. Okay. So what we do is we want to show that this ball this product ball sits inside here, right? Because then these are basis elements in x cross x, and so that would show this is open. Here, remember, and we showed that for exam 1. We know the basis elements of x because x is a metric space, and so if we put them together, this is the basis element for the product space. Here. Okay, so let's argue that. Okay, so what I'm going to do is I'm going to pick an x prime, y prime in this product set here. Then we know that d of x prime is less than epsilon, and d of y prime is less than epsilon. Right? Because x prime is going to sit inside here, so the distance between it and x is less than epsilon. Y prime is going to sit inside here, so the distance between y and it is less than epsilon here. So that's what we have here. Now notice that the distance of x prime, y prime here, I want to argue that if I pick a point in here, it sits in here. So what I want to argue is that the distance between x prime and y prime are in this interval here. And that's where this is going to come into play, because we know we've created this to sit inside this interval, so we're going to be inside that interval. So using the triangle inequality, this is less than or equal to d of x prime x plus d of x y prime. This here is less than x into x prime is less than epsilon. But then what I'm going to do, notice I don't have a statement for this, but I can use the triangle inequality again. D of xy plus d of y prime. Right? This is less than or equal to this. And this is less than epsilon plus r. Remember the distance of x and y were r, and epsilon, which is r plus 2 epsilon, which notice is less than a. Or sorry, b. Right? This is where this statement came from. I wanted that r plus 2 epsilon to be less than b. So notice that I have an upper bound here. So if I pick a point in this set, I know that the distance between them is here. So now I need to argue that I'm bigger than a, because then I'll be fully in this interval. Here. Okay? And I always hate erasing the board mid-proof, but I'm writing very large today, so. Okay, so, and I guess we'll put a comma here to continue it on. Let's look at the distance of xy. The distance of xy by the triangle inequality is less than or equal to the distance of x prime plus the distance of x prime y. But using the triangle inequality again, I'm not going to change this, but notice that this is less than or equal to the distance of xy. This is x prime, y prime plus distance of y prime, y. Hence, I can shuffle things around. Notice that I want to isolate this, so the distance of x prime, y prime is greater than or equal to. I'm going to leave this over here, and I'm going to move this and this over here on this side with this guy. Distance of xy minus distance of x prime minus the distance of y prime y, which is strictly greater than here r minus epsilon, which equals r minus 2 epsilon, which is greater than a. So now, hence, so therefore, maybe let's use therefore, x prime, y prime is in, therefore xy is in this open set, and it is fully inside this inverse image here. So we've argued that this fully sits inside of there because we took a generic element and argued that the distance was between A and B. Okay, moving on, we should also know what it means to be compact here. So we should know what it means to be compact here. Okay, so what does it mean to be compact? It means if we have a family OI of open sets with I in some indexing set such that the space is the union of all of these OIs, then we can find a finite subcollection or subfamily, and we'll call it OI1, OI2, OIN, with X equals the union of OIK here. Right, so it still covers, so this finite collection still covers. Now notice here, a lot of times we use our grammar. Remember that we can find is a there exists statement, right? If we have a family, this is a generic statement, this is a for all statement. So for any open cover, there exists a finite subcover here. Right? A nice example to look at, I'm not going to work this in the video here, but let F go be a mapping from X tau to Y tau 1 be a continuous surjective map if X tau is compact, then it must be the case that Y tau 1 is compact. And you can find this example in the book. This is on page 181 here. This is a very, very nice statement that says the image, the continuous image of a compact space is compact. We've used that a lot here. That's a really nice statement to know and be able to prove. Okay, so know this. You might see it. It's a really nice example here. Okay, let's look at another example. Let A be a compact subset of a Hausdorff space. We'll call it X tau. Then A is closed. Okay? So subset of a Hausdorff space is closed. Okay, so let's prove this. Note that the book argues through method of limit points. So the book shows, and this is on page 183, the book shows that A is closed by arguing that A contains all of its limit points, right? Remember, if the set contains all its limit points, the set is closed. Here. So we will argue A is closed by showing X minus A is open. I always like these open arguments. I don't know why. There's no reason to rhyme. I like showing complements are open to argue closed when it's possible here. And to do this, we're going to use corollary 3.2.7 found on page 82. So go back and take a look at that corollary. It allows us to argue that a set is closed by arguing the complement is open using neighborhoods. Here, okay? So let's start the proof. So let X be an element of the complement. And what we want to do is we will show there is a neighborhood n of this element X with n fully sitting inside X minus A, inside the complement. And that's exactly what corollary 3.2.7 states. Okay, so now notice, now for each A, in A, there are disjoint open sets. We'll call them UA and VA with X in UA and A in VA. And this is because X tau is Hausdorff. So notice that X is in the complement, so X doesn't equal A for all of these A's. So we have disjoint open sets where X is in one and this A for each A is in the other. Here. And let's put since X tau is Hausdorff. Okay, so notice that A is a subset of these VAs, the union of these VAs, where A is in A. So this is creating an open cover of A. Here, okay, well, what do we know about open covers of A? A is compact, so there's got to be a finite subcover. So is an open cover of A. Therefore, since A is compact, there is a finite subcover BA1, BA2 to BAN with A subset of these BAIs. Here. Okay, so define n to be the intersection of these UAIs, because for each one of these VAIs, there's a corresponding UAI, so let n be the intersection of those. Clearly, x is an element of n, and it's easy to see, and you can finish this off, that n is a subset of the complement here. It's easy to check that. So because I'm out of board space, I'm just going to put clearly this is true, but it's a quick little argument to argue that this fully sits inside of here. Okay, so what we've done is we've found a neighborhood of x with it sitting inside there. So therefore, the complement is open, showing A is closed. Hence, x minus A is open, showing A is closed. Okay, and then just a couple more things, and we'll end the video here. Hopefully this kind of gives you a couple practice problems, some things to think about. You can add to your little note card, your little cheat sheet here. Product topology. We've used it, we should know the definition, right? What do open sets look like? What is the basis? Here, so some things to think about for the product topology. We also discussed from the product topology these projection mappings. Onto the factors of a product. All right, we use these a couple times here. These are continuous. Remember, these were our PIs, which went from the product space to the factor. These are all continuous. And we should also know, this is kind of a big statement. We didn't officially prove this. It's a very detailed proof. The book argued it. But that compact subsets of Rn with the standard topology must be closed and bounded. That's a really large statement right there. So it gives us a way to view compact subsets of Rn, of Euclidean space.